Let's finish off this section now by taking some time to look at how to draw a comprehensive graph of a polynomial function. Now, a comprehensive graph has to have all the following features. We've talked about these briefly before. We have to identify all the x-intercepts, all the zeros. And we do that with our synthetic division, our factoring, our rational zeros theorem in order to completely factorize and get all the zeros or solutions for the polynomial for our x-intercepts. For our y-intercept, it's really easy. It's going to be when x equals 0. Then we locate all the turning points. Those we look for, or we're going to estimate those. We're going to estimate the turning points by using test points between each zero. And that allows us to get an idea of where our turning point is going to be located. And then we want to have enough of the domain to show end behavior. So we're going to be probably looking at a test point past the most extreme intercepts so that we can determine our end behavior is correct. So we're going to draw a comprehensive graph of each of these polynomial functions. And so we first want to start with our x-intercepts. Well, they give us one of our x-intercepts. They say that 1 is a 0. So we know that we have the x-intercept 1, 0. And so we can actually go ahead and plot that, 1, 0. Well, then we're going to use that 0 with synthetic division in order to find or get our quadratic equation so that we can find our next two zeros. So we're left with the quadratic 2x squared plus 7x plus 6. And so now we just need to factorize it and get our two zeros. So using our factoring methods, we end up with 2x plus 3 and x plus 2 for our factors. So we go ahead and set each of those factors to 0. We solve. And now we have our last two x-intercepts. -2, 0. And -3 halves, which is about 1.5, or is exactly 1.5. So we have -2. If here's -1, we've got another x-intercept at 1.5, so right here. Now keep in mind, we're going to have a turning point between each of these zeros, somewhere kind of in the middle of each of these successive zeros. Next, we're going to find the y-intercept. Y-intercept is when x equals 0. Well, the benefit of the y-intercept when we're dealing with a function in a general expanded form here is that every term gets canceled out by the 0, and so our y-intercept ends up being just the constant term at the end. And so that gives us an easy point to plot, 0, -6. So we have our x-intercepts and we got our y-intercept. Now we're going to look at the turning points, and we're going to estimate that by using some test points between each of the values of our x-intercepts. So we're going to use a test point about here, which is going to be -1.75. That's between -2 and -1.5. Let's use a test point. We could use anything in the middle here. It doesn't have to be perfectly in the middle, so let's just use a test point of, let's say -1. That'll give us close enough. If we want maybe a little bit better, let's actually do -0.5. That'll give us a better estimate of -0.5. So let's figure out that. And then between 0 and 1 of 0.5. So we're going to evaluate each of those functions. Let me do that in a different color here. So we're going to evaluate f of -1.75. We're going to evaluate f of -0.5. And we're going to evaluate f of 0.5. Now I've got our calculator here to help us out a little bit, but just remember that when we want to evaluate a function, our remainder theorem states that the remainder of the synthetic division for a given value gives us the function, what the function evaluates to at that point. And so what we can do is do synthetic division with each of these values, -1.75 and do our synthetic division with 2, 5, -1, -6. Now we're doing decimals, so we can use the calculator to kind of help speed it up a little bit, but we're just going to be doing addition and multiplication repeatedly. And so we'll take 2 and multiply it by -1.75 to give us our -3.5. Then we add 5 to that. We get 1.5. Then we multiply it again, -1.75, to give us the -2.625. And then we add -1 to that. We get -3.625. Multiply again by -1.75, doing that multiplication every time. And then we add it to -6, and then we get our remainder. So we have the 6.34 approximately, which gives us a remainder of 0.34, which is approximately 1/3. And so we have a point that is approximately at -1.75, comma 0.34. And so we can plot that point. So we're going to be plotting it here. And so it's not going to be very far up the x-axis or up the y-axis. So we're going to have this point just very, very close. And we see that turning point happens quick between those zeros. So we'll go ahead and do the same thing with -0.5. We'll do our synthetic division with -0. Did not mean to make that negative. -0.5. 2, 5, -1, and 6. And remember, this is just 1/2, so it's pretty easy to work through. So we've got 2. Half of 2 with negative is going to be -1. We get 4, -2. We get -3. And then we multiply and we get +3/2. And so we end up with -4.5. So that's more consistent. So we got -4.5. So I'll move this out of the way. If it'll let me. I guess it won't. There we go. Move that out of the way. And so we get -4.5. So again, we have the ordered pair. -0.5, comma, -4.5. And so that puts us at a point right about here. And then at 0.5, we'll do the same thing one more time. Half of 2 is 1. Add to 5 to 6. Half of 6 is 3. Add to -1 for 2. Half of 2 is 1. And we get -5. So our last point is 0.5, comma, -5. Which, again, puts us right about here. 4.5 is probably going to be a little bit higher. There we go. All right, so there we've kind of got our graph. Now we just need to consider kind of the end behavior. And we could test some points if we needed to, but I don't think we quite really need to at this point. But looking at the end behavior, we have an odd degree polynomial. Our odd degree polynomial tells us that we're going to be going in opposite directions. And because our leading coefficient is positive with our odd degree, it means that from this rightmost intercept, we're going to be going up. We're going to be going up and to the right forever. And from this leftmost intercept, we're going to be going down and to the left forever. And so with that in mind, we're going to go ahead and just try to connect this as smoothly as possible. And it's not going to be perfect, but it'll be close enough for us to be able to identify the graph correctly. So we just carefully smooth all of this out as best we can. And there is our comprehensive graph of our function. Now we can go ahead and we're going to do it one more time with the next example. First we start with our x-intercepts. We're given 2 as a 0 with a multiplicity of 2. So we know that we have this multiplicity of 2 of 2, 0. And remember that multiplicity indicates that we're going to have a kiss point. We're going to touch the x-axis, but we're not going to cross it at that intercept. So we need to remember that when we're plotting this point at 2, 0, it's either going to do this or it's going to do this, depending on where the other zeros and the turning points are located. A couple things we can also note is that we have a 4th degree polynomial and a positive leading coefficient, so we know our end behavior is going to go up in both directions. So now what we need to do is just find the other 2 zeros. So we'll use synthetic division with 2, and we'll be able to do it twice to completely factor down to our quadratic. Notice we're missing the cubic term as well as the linear term, so we need to have placeholder zeros in for those. We've got our remainder of 0, so that one checked out. Now we'll do synthetic division again with the second 0 of 2 that we have. And we're left with x squared plus 4x plus 4. Now, x squared plus 4x plus 4 is a perfect square trinomial, so it factors to be x plus 2 squared, which means now we're actually going to have another multiplicity. When we set the factor equal to 0, we get an x value of 2 with a multiplicity of of 2. X equals negative 2 with a multiplicity of 2. So we're going to have another multiplicity located in that kind of kiss intercept at that location. All right, next we want to find our y-intercept. Our y-intercept is nice and easy. Let's separate that there. It's going to be that constant term. When we evaluate f of 0, that term and that term cancel out, leaving us with just the 16. So we have a y-intercept at 0, 16. This point up here. And then we know from these zeros, based on our end behavior, that our graph is going to just kind of go off in either direction here. And so we just want to see if there's any weird behavior between our two intercepts that are given. And so we can use some test points of -1. We can evaluate f of 1 and f of -1 just to make sure that our graph behaves the way that we expect it to. So we're going to look at doing 1 with our synthetic division. And again, note here I'm using the original polynomial for the synthetic division. I'm not doing any of the factored forms. And so here we get a point at 9. And then if we do the same thing with -1, the same thing happens, and we get a point at 9. So we have 1, 9, and -1, 9. So we have symmetrical points there. 1, 9, and -1, 9. And so we know our end behavior is going to go up into the left and right on both sides. And so we're just going to go ahead and let's go ahead and do some quick test points on 3 and -3 just to see how quickly they're going to rise. So let's evaluate f of 3 and also evaluate f of -3. And based on the information before, we should end up with some symmetrical points on either side, seeing that we have this symmetry on the y-axis with every other point so far. And so f of 3 equals 7. So we have the point at 3, 7. And we're going to have that symmetry on the left as well if we checked it with synthetic division. It's going to be symmetrical. And so we've got our end behavior tracking correctly, and we just want to try and smooth out the curve as much as possible. We have a very steep slope all these points are very closely related or very closely on the x-axis. And so we have that bounce up because of that multiplicity. We come down to the y-intercept. We want to loop right back down around. And we're going to have that bounce again because of the multiplicity and come right back up. Not the prettiest graph, but it does give us a really good picture. And if we ever wanted to add more accuracy, we would just add in more test points like we did here in order to get a better picture of what our graph would look like. But we have all the key features that we need to identify to consider this graph comprehensive. And what I've done is I've shown on Desmos what the graphs look like in 100% precision, and it looks like our drawings are pretty accurate compared to what the graphing utility has given us.